Okay, today we're going to talk about Chapter 3, Section 2, and we're also going to go delve into Section 3.5 as well. We're going to talk about Rolle's theorem and the use of the mean value theorem. Now, warm up. I want you to explain why the mean value theorem does not apply to the functions given below. Well, this one right here, it says not differentiable. So I'm going to write down here, not differentiable. I know I misspelled T, and I'm not testing you. I just had a brain fart, so I'm just going to go ahead and erase that part right there. There we go. Okay, now, the next one. Why is it not different? Does the mean value theorem not apply? Because it's not continuous. Right. Okay, now, that's that one. All right, I went ahead and worked the next one here. It says find any critical numbers for the function, and in order to do that, you got to take the first derivative, which when we do that, we use quotient rule, and you could follow the work right here, but it ends up with -4 times x squared minus 1 all over x squared plus 1. Well, we got to figure out what the zero values are. Well, the zero values are from x squared minus 1, which if you factor that, it's going to be x plus 1, x minus 1. I can even write that over here, -4 times x plus 1, x minus 1, all over x squared plus 1. And then you solve for x, you're going to get x equals 1 and x equals -1. All right, now. Okay, real quickly, we look at the following. It says locate the absolute extrema on the function. So f of x equals -x squared plus 3x minus 5 on the interval from -2 to +1. Well, we do f prime of x, you get -2x plus 3. Well, when you solve it, you get a critical number of x equals 3/2. Well, if you look, 3/2 is not in the range, so we can't actually use it as a critical number. So we have our two endpoints, which are x equals -2 and x equals +1. Well, when we plug those in, we get -2, -15, so that's going to be our relative minimum. And then 1, -3, that is our relative maximum for this given situation. All right, now, that's that so far. Now, let's talk about Rolle's theorem for just a couple minutes. Okay. Let f be continuous on the closed interval from a to b and differentiable on the open interval from a to b. If f of a equals f of b, then there is at least one number in AB such that f double prime of c equals 0. Let me say that again. If f of a equals f of b, then there is at least one number in C in the interval from a to b such that f prime of c is going to be equal to f is going to be equal to 0. Okay, now we're going to use Rolle's theorem in order to determine the value of c on which the function on the interval for which f double prime of c equals 0. So let's look at that. When you do f prime of x, you end up with 4x to the third minus 4x, which when you factor that out, you get 4x times x squared minus 1. And then your three values are 0, 1, and -1. So if you look, you're going to have three different values at which f double prime equals 0. All right, we'll talk about this here in a little bit. All right, now, if you look at the graph, though, it's somewhere in between All right. So there you go. You get a look at that. Now let's talk about the mean value theorem. Okay. Mean value theorem says if f is continuous on the interval from a to b and differentiable on the open interval from a to b, then there exists a number such that f prime of c equals f of b minus a of b minus f of a all over b minus a. All right. Okay, this is kind of a tricky problem, but I went ahead and wrote it out for you. Now, here, I'm going to read it for you, then we'll talk about what it all means. It says 2 stationary patrol cars equipped with radar guns are 5 miles per hour on the highway. As a truck passes the first patrol car, he is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. Prove that the truck must have exceeded the speed limit of 55 miles per hour at some point during the 4 minutes. Okay, so here's what we need to know. Time. The time is 4 minutes, but in terms of hours, that's 1 over 15. So we have to put everything in terms of hours. Okay, so it's 1 over 15. Now, the average speed between those 5 miles, now this is an S. That's position. The position at the final position, which is at 1 over 15, minus the initial position right here. So let me write that down. S of 1 over 15 equals the final position, and S of 0 equals the initial. Okay, now 1 over 15, that's the final time over the initial time. And the initial time is 0. So it's going to end up being the position, final position minus the original position, which in this case is 5 miles apart. So this time it's 5. So I highlighted those. And then the final time is 1 over 15. Well, when you do the math, you get 5 over 1 over 15, which is 75. So we're saying that's an average, that the trucker had to average at least 75 miles per hour. And I apologize for dropping that. So, oops. Per hour. So at some point in that journey between checkpoint 1 and checkpoint 2, it had to. Now, that's an example of the mean value theorem. And we'll talk about that more in the coming time. Okay, next thing I'm going to talk about is what's called, and this is from section 3.5 on curve sketching, oblique or slant asymptotes. Okay, sometimes you will have a horizontal, sometimes you have a vertical, but in this case you will have what's called a slant asymptote. And its diagonal serves as the barrier guiding the end behaviors of the function. Now, somehow it's going to look something like that. Now, that's an approximation, but how do we determine the equation? Well, let's look on the next slide. In order to find the equation, you must use a technique learned in Algebra 2 called polynomial long division. Now, you have done long division before. You did it then. So we divide the top, which is 3x to the third, minus 2x squared plus x minus 4, and that's divided by x squared minus 2x plus 1. So when we do that, we divide and we get 3. You end up with, and you can see all the work here, you end up with 3x plus 4. Now, only the non-remainder portion of the quotient is your Lyne's equation. So that's this part right there. This part is your slant asymptote. If you have questions on how to do long division, let me know. We'll talk about it here in class or on a Google Meet. All right, now, example 2, analyze each function by finding each of the following and then sketch its graph. Find the x and y intercepts, find any symmetry that the graph possesses, that could be optional. The domain, that's optional. Anywhere it's discontinuous, equations of vertical, horizontal, or slant asymptotes. The intervals, whether it's increasing or decreasing as done by the first derivative test. Relative maximums or minimums. Intervals of concavity as indicated by the test for concavity or any points of inflection. So we did that right here. And I'm going to pause it for a moment so I can write this down. Okay, so here's what we did. We went ahead and did the first derivative, which we got negative 10x over x squared minus 4 squared. And with the second derivative, we get 10x squared plus 40 all over x squared minus 4 to the fourth. Okay, We also got that the intercept is at 0, -1/4, and that's just from graphing it. And we got the vertical asymptotes are at -2 and +2. And we got that from down here because if you factor that, it's going to be x plus 2, x minus 2. So those are vertical asymptotes. Now, the critical numbers are also when we do the first derivative test, are going to be 0, 2, and -2. And then there's a horizontal asymptote at x equals 1. And I kind of messed up on my graph a little bit, so I will fix that here in just a moment. But I want you to get the right idea. So I got my interval from -infinity to -2, and then from -2 to 0, and then at x equals 0, I've got that. I'll talk about that in a moment. From 0 to 2, and then from 2 to infinity. Now, when I plug in my numbers, y prime on this interval is positive. On this interval, y prime is positive. Here, y prime is negative, and y prime is negative. You got to find a test value in that range and determine that. And the best way is just type in the first derivative into your graphing calculator and do it that way. Now, for the second derivative, which is right here, you do the same thing. You do your test values, you determine that it's positive, and you determine that this is negative for this interval, and that this is negative, and then that is positive. And that's once again by determining a test interval in that range and plug it in your graphing calculator. All right, now, because y is positive and y prime is positive as well, y prime tells you that the function is increasing, which is true. It is increasing, and it's concave up, which you can see right there, concave up. From -2 to 0, from this point to right there. And I'm going to go ahead and highlight these critical numbers. They are -2, and then you got 0 right there, and then you got 2, which is right here. But if you look from -2 to 0, it's increasing, but it's concave down. From 0 to 2, it's decreasing, but it's still concave down. And you can see that right there. Because it's negative, decreasing, negative, concave down. And then finally, from 2 to infinity. From 2 to infinity, right there, it's decreasing, and it is concave up because y prime is positive. All right, so I'm going to go ahead and stop at this point because we're going to run out of time. And there is another one on there, and I'm just going to show you. I'm not going to go over it on video, but I will go ahead and finish it up for you so you have what that's going to look like. And that will conclude section 3.2. We'll talk more about this stuff in 3.5. All right, so